Liz, thank you for joining us today. Dr. Liz McDonald is a heliophysicist working remotely for NASA's Goddard Space Flight Center. Dr. McDonald has been studying the glitter of the Northern Lights for over 25 years, and it never ceases to amaze her. This has only increased over the last 12 years working with fantastic photographers and passionate volunteers. She leads a participatory science project called Aurora, which enlists people to help with community reports using smartphones and social media. So those of you that are looking for citizen science projects, that sounds like probably a good option. In 2018, along with a large team, including many amazing Canadians, they announced a new understanding of an unusual aurora called STEVE, or Strong Thermal Emission Velocity Enhancement. She has also led teams that build instruments to measure charged particles in the space environment for NASA and DOE satellite and rocket missions. She also serves as the NASA headquarters participatory science community as the lead of the Heliophysics Strategic Working Group on Citizen Science. Outside of work, she likes to ski and hike and use iNat and Merlin. Merlin's a great app too. But yes, that's enough of that, or me as well. Liz, I'm going to hand it over to you and mute up. Thank you.
Okay, thank you so much. I'm really excited to moderate this conversation with my colleagues from the Space Weather Prediction Center. Before I do that, I'm going to share just a little bit more information about Aurora with you all and invite you to join us if you might like to get involved that way as well. This is a project that is serves as a bridge between the scientific community and the enthusiast and citizen science and photography community. So I know how amazing each of these communities are, and am excited to bring people together today. In terms of the Aurora and the recent historic storm that we had in May, and if you are interested, if you missed it, or if you are interested in learning more about that, that's what our project can help with, as well as help in resources for educators about auroras and things like that. So we do utilize models from the Space Weather Prediction Center that we're going to hear more about. And help people get location-based alerts for when the aurora might be visible near them, as well as they can report directly on our map and help others see where it's actually happening. So that was really useful during this historic storm where people received alerts even into the far southern United States. And we are having an event coming soon where if you have some aurora photos that were captured recently in May, or perhaps even more recently than that, we're having a public event and it's going to be a fun event. So I wanted to be sure to invite any aurora enthusiasts who are out there today. We call it our Reportathon event, where people can still submit those unusual, rare photos for science. And we also have the chance to win some prizes like this scientifically accurate Aurora hat that we have recently blogged about and is a creation of my colleague Laura Edson, who is also in the chat and helping share links and answer questions about Aurora and this event. So if you all have any questions about that, we're happy to talk to you there. But without further ado here, definitely want to get to our panel, and am excited to join to hear more about space weather and the forecasting behind the aurora and what's going on. So we have an esteemed panel joining us today. That includes Bill Murtaugh, who currently serves as the program coordinator for the National Oceanic and Atmospheric Administration, NOAA, and their Space Weather Prediction Center, also called SWPC, in Boulder, Colorado. And Bill is NOAA's space weather lead in coordinating preparedness and response efforts with industry and government agencies around the world. He also advises on policy with space weather policy with Congress and the White House. So that's Bill. And then we also have Dr. Sue Feng, who is a space scientist with the Space Weather Prediction Center. She is an expert in modeling of the upper regions of our atmosphere, the thermosphere and ionosphere. And she leads that program at SWPC. And serves there developing several models and product development teams, leading several of those teams to fulfill the requirements for the Space Weather Forecast Office in that area. So she will be telling us about research, the research community's needs there, and analyzing space weather's impact on customers from multiple domains, whether they're satellite or aviation or GNSS or GPS services, industries. So thank you. And also we have Mr. Sean Dahl, who is an Air Force retiree and spent most of his military career in meteorology and space weather. After retiring in 2007, he held several meteorological forecasting positions with the Air Force and the National Weather Service until 2015, when he became a physical scientist and senior space weather forecaster with the Space Weather Prediction Center. And now he is SWPC's first service coordinator and leads decision support services issues there and products, and manages education and outreach initiatives, and many other things there. Sean has been married for 34 years to his lovely wife, Cindy, and has 2 sons. So I will turn it over to my colleagues from NOAA, and we're very excited to hear from you today. Thank you so much.
Thanks very much, Liz. Appreciate that. Glad to be here. Just in case you're wondering where Bill Murtaugh is, he's actually here with me today. So when he comes in, it'll still may say my name, but it will be Bill. With that, Sue, thank you for driving the slides. Please, next slide. So what is space weather? Well, the quickest I can say it is what's taking place on that giant sun of ours 93 million miles away in that huge vacuum of space between the sun and the Earth, and ultimately at, here, and around our planet. And we at the Space Weather Prediction Center are really focused most of the time, at in and around our planet. Next, please. What are the things we're looking at? Well, there's many different things that we're forecasting, but there's 3 primary areas. And these primary areas relate to the NOAA space weather scales, which Bill will talk to a little bit more in detail because we're looking at revising the way that's done. But right now, these are the 3, and they revolve around the impact. So the impact being solar radiation storms, HF radio blackouts, and geomagnetic storms. The underlying cause is what we're trying to forecast here at the Space Weather Prediction Center. And that would be the solar energetic particles in the form of protons, the solar flares, and coronal mass ejections and coronal holes. We're not going to talk about coronal holes today, but we will focus on these other 3 things. Next, please. So what is it about the sun? Why are we hearing so much about it right now? Well, because there's this thing called the solar cycle. Roughly every 11 years on average, we go from a period where we have a minimum of activity up to a peak of activity and back down to a minimum of activity. That's the solar cycle. That's what happens roughly every 11 years. Right now, we're in and around solar maximum. It'll be decided when we officially reach the peak. It may not be yet. It could be as late as early next year, but we are in that realm right now. So a lot more activity has been happening. A lot of this has been making the news because we've had some pretty extraordinary events. The plots you see on the bottom here are some of our solar cycle prediction plots compared to where we're currently at. There was an international panel of experts about 5 or more years ago that predicted the solar cycle. They thought it would be similar to the previous cycle, and that light pink shade is what the prediction was. Well, you can clearly see in the darker shades above it now that forecast has had to be revised by some great work that's been done here in part as well, because the solar cycle has been so much more active. We've had one of the largest numbers of sunspots we've seen in over 2 decades, perhaps, here in August as well. We've already experienced the top of our scale on the geomagnetic activity. And it doesn't mean it'll turn off when we reach a peak, by the way. It's slow to come down. So it'll take all of this year, all of next year, and even to 2026 that we will continue to be at an increased risk for some of these more extraordinary events. What you're seeing with the sunspots is part of that cycle. These are strong magnetic fields that come puncture through the surface of the sun as all part of the solar cycle and the dynamics that go on. And that's where we start as forecasters looking at these sunspot regions, because they are usually the most likely source for some of these storms that we're talking about today. Next, please. Solar flares, a blast of energy coming from the sun, speed of light stuff here. Now we can predict the probability that these flares will happen and even how strong they may get based off things we're analyzing and looking at, but we never know that a solar flare is imminent. We have no way of knowing that one is about to happen. So we cannot put a warning out for these. And it's speed of light. So when we see it on our GOES satellite that's looking at these, or the NASA research satellite, the Solar Dynamics Observatory, the effect is already on the sunlit side of our atmosphere. And this affects some of the certain radio waves that we communicate in. Aviation, emergency response, these types of things still use these frequencies among other hobbyists. But in emergency situations, this frequency can become very useful and needed and critical. And the effect can be immediate. Sunlit side of our planet can have an impact. The stronger up the scale it goes, the broader that geographical area goes, where you get into the R4s and 5s, pretty much the entire sunlit side of Earth is going to have an impact, and HF radio communication can be very difficult, if not impossible. Next slide. Solar radiation storms, kind of a frightening word. This is what relates to the solar energetic particles. So remember, a solar flare was energy released in the form of light. We measure them in X-rays with our GOES satellite. This is particles now. So they're a little slower, but they can still be very close to speed of light stuff, depending on where they happen on the sun. For solar flares, it doesn't matter on the sun where it happens. If we see it, the sensor sees it, the effect is on the sunlit side of our planet. These work a little differently. But when they come from the sun, they drive up the scale as well, this 1 through 5 scale. We've already experienced an S3 level storm this year, although it was very brief in duration. It did cause us to send out warnings and discussions with NASA for the benefit of the astronauts in the space station, as well as the aviation industry, this can affect in and around the polar regions on their flights across those oceanic regions for shortcuts. These can also mess with satellites. They can cause anomalies to happen within the electronics and make a satellite inoperable in the worst case scenario, although that's very rare. It doesn't happen often, but the higher up the scale you go, by times of 10, each number on this scale. We start off at 10 of these particles, so an S2 would be 100, and so on. So you can see when we get to the tens of thousands of them or more, when there's usually less than one out there, this can become problematic for satellite operators. And Sue will have a little bit more information about these as well here as we go on. Next slide, please. All right, so now let's get into the coronal mass ejections. These fancy sounding word, right? CME for short. But essentially, these are large explosions of solar material and a strong magnetic field getting ferried out into space along with it. These are the slowest of the batch that can head here towards Earth. The fastest they can get here is about 15 to 18 hours, but usually it takes about 2 to 4 days. But these are the ones that interact with Earth's protective magnetic barrier, our magnetosphere, and can drive up this thing called geomagnetic storming. But when we see these CMEs, the only way we really know that a CME for sure has happened, and the way we can analyze its structure and try to determine whether it's going to arrive here at Earth, and if so, how strong it might be, is by a satellite in space that has a coronagraph on it. And this is a NASA research satellite that's been out there for decades, 1 million miles from Earth. And that's our sole measure. The good news is we now have a new compact coronagraph out there, I think Bill will mention too a little bit, that NOAA owns. It's on a GOES satellite, GOES 19, and that's going to be operable before the end of the year. So we will have real-time coronagraph imagery coming into the Space Weather Prediction Center, allowing us to do better predictions and more timely predictions at that. Next slide, please. So what is this thing called a geomagnetic storm? Well, this is what Aurora enthusiasts are most certainly interested out of everything that we're talking about here. But so are many of the sectors, the technological infrastructure operators, because this can be the most impactful and effectual across all these different sectors, from satellites in space to the power grid here in our country, or around the world for that matter. So this interacts with Earth's protective magnetic barrier. But there's something that really has to happen to really drive up things to levels that you see on the bottom here, these G4s and G5s that we experienced in early May, followed by a long string of G3s. We had over a 24-hour period of time with multiple CMEs, and this is usually when this happens, these types of events. In the ones in early May, that I'll focus on here shortly, we had at least 5, perhaps 7 that were in the direction of Earth, and some of them caught up with others, and we had this long duration event. But we have to have the proper orientation. Remember, I talked about magnets, magnetic fields localized, causing sunspots, magnetic fields stretching out into space with these CMEs. Well, we have this another satellite, 1 million miles from Earth. It's another NOAA operational satellite called Discover, and an old NASA research one called ACE, and that's what we use to measure the solar wind out there. That's when we can see the arrival of these events. So one of the things it measures is the magnetic field, not only how strong that magnetic field is, but what's its orientation. So Earth's magnetic field is pointed north, comes out the bottom of our planet and goes into the top. So it's pointed northward. Along comes a CME. If it's the same direction as Earth's, yeah, you'll get an initial reaction, things will spin up, but then they may settle down fairly quickly because it's like repelling, trying to put 2 negative magnets together. But if it turns south, the opposite Earth's, or arrives south and stays that way like happened in May, it's connected. All these things can spin up very quickly. And you can see we went from that green color on the bottom plot, which was quiet conditions, to a G4 in less than 3 hours. That's the impact the CME had so quickly because it stayed south that entire driving train through. And I'll talk more about some measures we do behind the scenes, but I've got G3 highlighted there because that is the level in the middle of our 1 through 5 scale for these storms that we talk to the North American power grid. Next slide, please. So here's the behind the scenes, behind the Aurora that everybody's enjoying out there. These are the actions that we at the Space Weather Prediction Center are doing. And much of this is decision support related. We're not only sending out the warnings and alerts saying things have happened, or the watches for long, range events, forecasts. We're picking up the phone and making phone calls, interacting through social media, through media applications with not only our core partners and people we coordinate with, but with customers out there. This whole litany of things you see spelled out on this, from the U.S. Air Force to space launch, all the way down to the NSC, which is National Security Council, and WHSR, which is the White House Situation Room. This is what we're doing at the Space Weather Prediction Center. Some of us in the forecast office making direct calls, others like Sue A talking to satellite operators, Bill talking to the White House, our director, Clinton Wallace, talking to the White House as well, or National Security Council, and so on. FEMA gets involved when we're talking about 4 levels on 2 of these types of events. And then when there's a 5, they're messaging that down. So things can really escalate quickly on how the information is flowing. So the best thing for people to do with a talk like this is know to go to the Space Weather Prediction Center, our webpage, to find out what's really going on out there when things start to spin up in the news. One thing I'll focus on here, because it relates to the geomagnetic storms and the power grid, is that North American power grid entry. So when we get to a 1 on our scale, and let's not forget there's levels below the space weather scale that are important. Think of the hurricane scale. You have tropical storm force winds, that warrants a warning, but it's not a hurricane yet. Same here in space weather. When you get to a certain level, okay, now it warrants NOAA space weather scale attribution. So when we get to a 3 on our scale, we're picking up the phone and initiating a hotline call with basically most of the North American power grid, all the southern Canadian provinces through the mainland 48 United States. All get on that phone call through their reliability coordinators. We tell them what's going on, what to expect, and this is what we do when there's a warning, and then whenever we reach those levels, it's called an alert that we send out, and we call them again. What was different in May was we did something a lot more proactive, and I'll dig into that here shortly. The next, please. Here's the normal sequence of events, just so everybody understands, because we've talked about a lot in a very short time. Solar flare, we predict all of these things in our 3-day forecast, all these NOAA space weather scale levels, but we can't warn, remember, on a solar flare, we can only alert on it when we see it because the effect is already here. And we send that alert at an R2. We don't do it for anything higher because these can go within a matter of seconds through most of the categories on that scale. So we alert at an R2 and then we summarize it when it's done. We send out a warning for radiation storms at just the S1 level of expectation, and then we'll alert at every single level after that. For geomagnetic storms, we do watches from the 1 through the 4 level. We don't try to do a 5 watch right now. And then we send warnings out up through the G3 level. We stop there. Once again, things can get out of control and escalate quickly. And then we focus on alerts, which we send out every 3 hours as these things happen, because that's when it's remeasured once again. And we'll do that for all 5 levels on that scale. Next, please. So let's talk about May. What was going on in the forecast office and SWPC as a whole throughout this event? So we had some pretty massive sunspot clusters on the sun. One in the northern hemisphere, you can see how the sun's rotating here. And then this giant one that emerged and grew in its, not only its appearance, but its in magnetic complexity. Some of these magnetic fields that cause these sunspots can get so complex. Think of magnets littered around that are warping and twisting and then bending over and popping through the same magnet. That's kind of what happens with these sunspot groups and their associated magnetic fields. So it was pretty clear to us as forecasters that these sunspot groups were concerning. They had a lot of flare potential, and we dramatically increased our flare probability forecast to pretty much be expected, meaning that was greater than a 70% chance of flares happening. The northern sunspot group was producing a lot of flares, but not any of these coronal mass ejections. The southern one, on the other hand, started producing coronal mass ejections as well as flares. Next, please. So here's the solar flares that were happening throughout this that week of May 8th through the 12th, that whole entire week before that even. And so we're alerting on all these flares over and over ago whenever they reach that R2 level. And then each of these flares, especially if there was a CME involved, we're looking at the potential for a radiation storm. In this case, there was one. It was just a minor one. It didn't get to the severe levels or anything like that. But we had to forecast those and adjust forecasts throughout this whole week as well as things progressed. But then, as I mentioned, the southern region started producing coronal mass ejections. Next slide, please. Now, we can't forecast coronal mass ejections. Certainly, we can figure that they're likely with a certain type of sunspot group like that one down south, but we don't really know when they're going to happen or if they did indeed happen until we see it in the imagery or with some of our critical core partners in the Air Force who mans a fleet of optical telescopes and radio telescope networks. These give us signatures and clues as well. But it's really the coronagraph in space that now becomes very important and critical. We measure these CMEs. You can see them exploding off the sun beginning later in that week until the CME actually arrived, one of them here at Earth, the multiple CMEs for that matter. And we're analyzing every single one of these, not only their symmetrical shape and structure, but put it into one of our models called the WSA-Enlil model, which maps out what direction these CMEs are going based off our analysis. If it'll arrive at Earth, if it'll be above Earth, below Earth, ahead of our orbit, behind our orbit, or right here at Earth. Well, in this case, you can see this nice circular shape. It was pretty clear these were aimed towards Earth. Our model confirmed that. So then we put out a watch. The first watch we put out was almost 2 days in advance, and it was a G3 watch. Pretty standard for CMEs. But as more CMEs happened, remember I said there were multiple CMEs here heading towards Earth, and one of them much faster than the others, it was clear this needed to be upgraded. So this got upgraded 24 hours at least in advance to a G4, the top watch. Remember, we have not put this watch out at that level since the year 2005. So this gives you an idea of just how rare this is and how concerned we were about an arrival here at Earth. Next slide, please. So what do we start doing when that G4 watch spun up and got put out? Well, we immediately start communicating with core partners, the government, departmental levels, on through the critical infrastructure operators that we work with very closely for decision support purposes, such as the power grid or the government, FEMA. We happen to have a tabletop exercise that was going on for a similar scenario, much more extreme than what we reached in the May event. but we were in place. I was down at FEMA Region 8 headquarters in Denver. Bill Murtaugh and Clinton Wallace and others were deployed up into the Washington, D.C. area on Wednesday of that week, going through a tabletop exercise, and then real space weather starts to break out by Thursday. So now we're doing real-time updates. FEMA has been a huge partner of ours and has become a critical element to messaging downwards to state operational emergency response centers. They could not have been more prepared because we had the exercise going on and then real space weather broke out. But this, by now, you've read a lot of the other things on the slide, and this is exactly the type of messaging that we're doing at the highest levels down to those critical core partners such as the power grid. One other thing I'll make a note of here is what we did different for this that ended up being very crucial was we notified the power grid well in advance this time. Usually we only do that when we hit the warning criteria, 15 to 45 minutes of lead time. We were very confident in this forecast and knew how critical this could be. So we notified the power grid that morning, 6 hours in advance. That allowed them time to get things ready, like other giant transformers to take a load if needed, other high voltage transmission lines ready to ferry things over if things were becoming degraded or detrimental. Bottom line is they started using those. Things were overheating. Things were getting to the point where they really had to do some pretty essential mitigation efforts, but they were successful thanks to our work here at SWPC and others in this endeavor. Next slide, please. So the events of May 8th through the 12th, we were continually messaging. We upped that messaging the more confident we got, even with the flares and radiation storms, on through the geomagnetic storm. When we hit that G5, other things spun up. Some things that we did in advance, I haven't even mentioned, there was so much. But as things escalated in the storm now was here in progress, we went really into decision support mode and any critical situational awareness updates that industry users needed, such as the communication entities around the world, the big ones that we all rely upon for our cell phone coverage or TV services. They wanted situational updates. And we're happy and proud to provide that so that they have the information they need to make their decisions to keep things running. Next slide, please. Some of the impacts that we had from that storm and effects, there was quite a few. You can see we're not just focused here in the United States or North America. Other areas around the world were experiencing issues with their power grid, with electrical flow. Aviation was diverting flights much further south. GPS was a mess for many users of that, including farmers in the rural Midwest, to the systems that are relied upon for aviation that Sue will talk more in detail about. Satellite operators were busy. She'll talk to that as well. Even the atomic clock was affected by the intensity of this storm. Let's not forget, even though we say this wasn't the worst it could be, this was a historical storm. It was comparable to the storm in 2003. Just much less impactful due to all the work that's been done that Bill will talk about here at the end. And with that, first, Sue is going to go into a little deeper dive here about the GPS and the satellite users and what we're doing to help them out. Sue?
Yeah, thanks, Sean. I think there are a lot of things happening behind the scene while people are watching Aurora. So as a scientist, as our center, what we are doing is really produce a lot of product at SWPC so that we can help the industry to make decisions. So I'm just going to bring a few examples. So one of this is the whole atmosphere model and ionosphere plasmasphere electrodynamic model. It's called WAM-IPE. It's operationalized at SWPC since 2021, and we did some upgrade last year summer. So this is the weather model from the ground all the way to 600 kilometers, and we provide the information all the way to 1,000 kilometers so that we can provide the LEO industry, the low Earth orbit satellite operator, some of the storm responses associated with the satellite drag. So there are a lot of other applications such as the GPS PNT and communication HFCOM can be provided by this model. So this animation shows here is we actually had some hiccup during the storm. There were settings the model energy was way beyond what we thought was happening. So we have fixed that operational model, and this is what we will see if you get to see the whole storm happening. You can see that energy coming in the high latitude, and you see the density increase in the color contour of the density. So imagining you are going through those areas, your satellite gonna increase the drag impact. And there are also very tremendous neutral wind that will go against increasing the drag component as well. So So there are a lot of aspects of space weather impact on satellite, not just the drag. We can also have a significant radiation impact. Luckily, this event doesn't have a huge radiation impact on a lot of satellites, especially LEO, and we did not hear any report at the geo orbit. However, we have different product and different plot that kind of go in real time to alert the community. So during a storm, my position will be really communicating with a lot of entities, especially those large constellations like Starlink and several maneuver tracking companies, trying to make sure that they understand the conditions, they know when things going to come down, they know how to mitigate the problems. So overall, we see a lot of altitude control issues from different industry, different companies with a report back, and there's an orbit propagation problem, the accuracy reduced significantly. Therefore, they need to dramatically change the collision avoidance procedures to avoid collision that is unnecessary. And there are also a lot of company has to continue firing the thrust so that they can do a very good, they can maintain the station keeping maneuvers so that they keep the satellite in the right orientation or in the right altitude to support their customers. And there are also several radar tracking company report some of the impact during the storms. So behind the scene, we are working very hard. We are in contact with several companies and trying to make sure they know how to make their decisions for next step. And we were also expecting the second storm coming from the Sunday, which actually was largely missed. So I think there are a lot of things happening behind, and we're all working very hard with different partners. And the other thing is very important is the GPS positioning, navigation, and timing, PNT, which also the same environment for the PNT also impact the satellite communication if you are in the L-band or frequency below GPS frequency. And this plot, I really like it. It's from one of the group from Stanford University, and it kind of lay out what the importance of PNT are being utilized in the modern world. So you can see you can be utilizing that in unmanned vehicles, over the ocean, over the land, and there are a lot of applications in the space domain as well, and a lot of agricultural applications. There are also a lot of different applications that maybe we have not utilizing a lot, and there are a lot of drone applications that nowadays being carried out in our society are also critical. So we also have different models that giving the nowcast information. Like this one is giving the global ionosphere density information. So you can see that with the storm going through North America has a significant increase of the density. Those sharp change of the ionosphere density can impact the signal accuracy when you have a signal going from the ground all the way to your satellites, any satellites. Once you go through that space, you have to consider the changes in the system. So some of these changes can directly impact several systems. So for example, for the aviation customers, a lot of times they have this system called wide area augmentation system. Basically what they do is they give the GNSS positioning arrow to the airplane from the satellite. So they calculate the arrow, send it up to space, and using the satellite to notify the airplane how much the arrow going to look like. And some of this example, you can see different storm in 2023. We saw this large-scale ionosphere density change directly impact this one. So in this plot, the red means the accuracy is decreasing, the capability is decreasing. This is just a distortion for that particular storm. And for this storm, before the event on May 9th, they have a good coverage over the whole day, averagely above 85% to almost 100%. Right due to the storm, we can see that the whole area has availability less than 85%, means that whole system is not capable of doing a lot of guidance landing and over the ocean correction for aviation customers. And then that last continues into May 11th. The accuracy is still not there. The variability is very less. And then till 12th, it still gradually come back to have this kind of vertical landing guidance system. So I think that impact is significant for aviation customers. So looking into the future, the model like YMIPE, which is pretty capable, we are working with a lot of industry trying to improve this capability. We are, first of all, we're going to work with, we are working closely with SpaceX Starlink to ingest some of this real-time data from 5,000 satellites to improve our capability and accuracy of the models. And we want to build an open source capability so that everybody in the industry can use it, including the government entities. And government has a clear policy that transfer all the collision avoidance satellite messaging system from DoD to DOC under the Office Space Commerce. They're actively building this track systems to provide the commercial collision data message in the future for satellite industry. We are working closely with them to see how we can integrate some of this information, environmental conditions into their track system. So there are a lot of future capability that we're looking into it. And I think I'm passing to Bill. I think there are several other activity we're carrying out as let's see right now. Back to you, Bill.
Great, Sue. Thanks. We're going to continue that theme that Sue finished on looking forward. You can see from the discussion so far that the impacts of space weather are quite diverse. So are the many, many challenges we have going forward to improve our services to the nation, indeed to our partners around the world. So let's talk we'll finish up just a kind of a positive note on some of the things, some of the big things that we're undertaking right now to do just that, to make this nation more resilient to space weather, to improve our products and services. Let's go next slide, Sue. So one of the things is the revision of the space weather scales. So most of our citizens understand what a Category 5 hurricane is or an F4 tornado. These scales were developed back in 1999 to be somewhat similar to those scales. So it's 1 through 5. However, note that date, 1999, a lot has changed. Space weather capabilities, our user base, so many things have changed in the last 25 years. The scales have not, and they need to. Next slide, please. And the event in May highlighted many, many reasons we have to update these scales. And I'm not going to go into all of them, but the storm that occurred in May of this year highlighted some of the problems we have. The storm on 10/11 May was a G5, but back in 1859, we had this famous storm we called the Carrington event. It too was a G5, but one was extraordinarily stronger than the other. The Carrington event was much, much stronger. And you look at that little plot or that little box there, you'll see the disturbance storm index, just as an example of the difference of intensity. Minus 412 was the May event. We think the event back in September of 1859 was 2, 3, 4 times bigger than the storm of May. So both of them would be G5, but really we're not capturing that intensity. So our colleagues around the world, especially the end users, the power grid operators, have pointed this out to us. They said, look at that bottom point I make there, the extreme, we call the G5 condition an extreme condition, but the power grid folks says, this is really not extreme to us. Sure, it's extreme if you're down in southern Florida and you look up and you're seeing the Aurora. That is very rare. As Sean said, it's been 20 years since we had a storm of this magnitude. But the power grid folks are using this thinking extreme means extreme impact on the grid. And that is not the case. So we got to calibrate these scales. And we're doing that right now as a 2-year effort underway. Began this year, will end next year. We're working with our colleagues around the world. A lot of countries have adopted these scales, and we want to do this in unison with these folks. And it's well underway, so stay tuned to see the developments and hopefully the improvements on the scales in the coming years. Next slide, please. So key new satellite missions. I mean, this is extraordinarily important. The backbone of the products, the models, are the observations. Sean mentioned that first one. GOES 19 just launched last couple of months ago, and it's going to produce real-time continuous coronagraph observations, which are critical for our geomagnetic storm forecasting for the Aurora prediction. But also next year, we're going to have the space weather follow-on. We're going to send a spacecraft out to the L1 point, 1 million miles out in space on the Sun-Earth line to ensure we have the continuity of critical solar wind measurements, as well as another chronograph. I do not want a single point of failure. So if I got a primary and a backup for these key measurements, it puts me in a much happier place. So this time next year, we're going to have 2 chronographs providing continuous real-time measurements of these coronal mass ejections, as well as the continued measurement of solar wind at that point at 1 million miles out from space, which is so important to us. Next, please. Transitioning research to operations. I know we've got a lot of folks here from the meteorology community that appreciate this issue of the challenges of transitioning research to operations. That issue very much lives in the space weather community as well. But we are doing a couple of things. For those who are aware of the test beds that we have a hurricane test bed, severe storm test bed, fire weather test bed. We are in the process of developing the space weather test bed. It is well underway. This is a brick and mortar situation here. We've knocked walls down. We're building this test bed in the space right beside the Space Weather Prediction Center, the Operations Center here in Boulder. And it'll be a great opportunity to work with end users, to work with researchers, scientists, the modelers, working together to improve services to support the nation. But it's not just a one government approach here. It has to be a one nation approach. So much of our modeling and science and research is done in academia and outside the government. So we now have new space weather centers of excellence have been introduced, working very closely with the government, again, all trying to improve services for the nation. You'll see that picture of all the folks there signing. That was an actual event at the White House, not just some months ago, where we had the leaders from the various agencies, NASA, National Science Foundation, and National Weather Service and Department of Defense, all agreeing to work closely together on improving this research to operations. It's critical to get us where we need to be. Next slide, please. And it's not just the science and the forecasting and the prediction. That's only so good unless we have the end users taking the right precautionary steps, the mitigation steps. What good is it, right? So we're working very closely with the response and recovery folks to ensure that they have the information that they can ingest, integrate into their operational plans so that they are doing the right thing during big space weather events. And I just wanted to point out that, and Sean had mentioned this, the partnership with FEMA is critical. That 2019 document, you see a picture of it on the right-hand side, is publicly available. It provides guidance to departments and agencies for development of their operational plans so they can continue their mission essential functions that each department has to serve the nation. And I also wanted to point out the National Risk, Threat and Hazard Identification and Risk Assessment, the THIRA 2019 document, it identified 2 natural hazards that had consequences for the nation. You know, we can have a Category 5 hurricane. It's a big deal, but it's local. It's regional impact. Same thing with an earthquake or a large tornado. But 2 things can have impacts, not just in the nation, but the globe. One, we just felt, pandemic. Second one that they identified was space weather. So it's very much identified by FEMA, letting everybody know in the emergency response community around this country and indeed around the globe, this is a serious threat. It needs serious attention. Next slide, please. So that's it. I'm just going to finish with that little conclusion, and it's an important conclusion. The spectacular won over consequential. That is the story we want to share every time we have a big space weather event, that we observe it, we predict it. The end users take the steps necessary to mitigate the impacts, and then, of course, the consequences are minimal, and we're left with this spectacular aurora that we saw in May, and that's what we want to be, is enjoying this show and not the consequences. So I'm going to finish at that. I hope that helps everybody understand, while that aurora lit up the sky all the way down to Florida and the southern states, an awful lot was happening at the Space Weather Prediction Center and space weather centers around the world to provide the information to the end users to make this nation more resilient during these big space weather events. So thank you, Liz. I'll turn it back over to you for Q&A.
Awesome. Thank you so much. That was wonderful and really a great tour through the impacts and the different timelines and the increasing, resilience of space weather coming up. I'm going to start right through the questions we have in the chat for you all. And we hope for more questions in the chat. There's some great ones here, but I think if we keep our responses to like 2 minutes, then we can keep going and get to more questions. So the first question is there a clear relationship between the sun cycle and some different cycles related to climate and weather? Sean, or who wants that one?
I'll take a stab at it. Sure. Nothing that's proven yet. There's science looking at that type of relationship. But for now, the best answer is we don't know. It doesn't seem so, at least not the solar cycle itself. Those changes are quite minimal when they happen, not enough to affect climate as a whole. But there are other studies in science going on investigating that over the long term.
Mm-hmm.
I will add that there have been some studies that are quite interesting on extended periods of low solar sunspot cycles. So during that period of 1640 to 1710, we refer to it as the Maunder minimum. People have been observing sunspots right back since the invention of the telescope in Galileo in the early 1600s. So people have been watching. It's the one historical record of sunspots is sunspots dating back to that period of time, the 1600s. But during that period, 1740 or so, or 1640, 1710, there was people were looking at the sun and not seeing any sunspots. And people have said that that has been correlated with the mini ice age. So it may have played a role. There was other issues that came into play with volcanoes and whatnot, but that study has been done and is quite fascinating. But outside of that, I think Sean is spot on. A lot more work needs to be done.
Okay, great. Thank you. And next question. We have a few links queued up for this one also, but wanted to put it to you all as far as there's many different indices, and Sean, you did a fantastic job just with a great plain language discussion of space weather. And there was a question during your talk about what is the KP index. So wanted to see if you had a great simple answer for that one too.
Sure, thanks. There's different ways that this is all measured. That's very true. Some of our partners use something called the AP index. We often do a lot of our forecasts for them based off that index. There's the KP index. For we here at the Space Weather Prediction Center, the KP index is really a reflection of 8 observatories around the world, magnetic observatories that are looking for deviations in Earth's magnetic field. That's compiled into what we look at as a real-time estimated index focused on KP. Now the KP is a 0 through 9, and each of those numbers, except for the top one, is divided into 3s. So you can have, say, a 4M, a 4Z, or a 4P. When we get to 5 on the KP index, that's where we're at G1 levels. Remember how I said there's levels that are critical? We send out a warning at KP of 4 for some users out there. When we get to KP of 5, now we're at G1. And so on until we get to KP of 8 and 9. A KP of 8M all the way through KP of 9M is a G4. KP of Z, the top of that KP index, is a G5. And as Bill said, that's the top. We can see how things are stronger based off deviations, but we no longer have a measure for it. So you have a KP of 9Z or a G5, and that's currently the top of that index and scale. So when we're doing a forecast, we do it by KP index, those 0 through 9 numbers. But whenever we have a G scale, we put it in parentheses on our 3-day forecast.
Okay, great. Thank you. And next, quickly, we have a question about what can electric utilities do to mitigate the potential impact from these storms?
I'll take one. Sean, you can give a second example. One is actually kind of counterintuitive. And a lot of times, especially during the spring and the fall, when the energy loads are lower, when we're not dealing with heat waves or big freezes, they will take some of the big transmission lines out for maintenance. So we've got those big 500 kilovolt lines running north-south from the lovely hydro-rich areas in British Columbia down along the west coast. They will do the maintenance during the spring and the fall in large part. When they get a heads up from us, there's a big storm coming, they stop the maintenance. They want to get the system as robust as possible. They'll bring those big lines back into play so they can better manage the induced current, that unwanted current that comes into their system. They're in a better position to manage it with the network up and running fully. So they'll cancel the maintenance and do what's necessary.
Yeah, and for just the G1 alone, we're making a phone call to a couple of transmission power operation centers up in the northern part of the country, just at a G1, for many of the reasons Bill's talking about. Maybe they just want to get a procedure ready to go, maybe have some manpower ready to go, check out the integrity of a transformer if things escalated quickly. For the event in May, as I alluded to when I was talking, some of the feedback results where they did bring some of these transformers back online because they didn't want the ones that were being used to overheat because temperature alarms were going off. So even though it was successfully mitigated, it wasn't to a level that had caused a catastrophic collapse. They were working hard. And if there had been a major heat wave going on, or if the storm had been too much stronger, they're not sure they would have fully made it through without some kind of issue.
If I could add just one more thing, that the activities on the power grid vary greatly because the vulnerability varies greatly depending on where you're located, latitudinal, your location further north, the geology, the ground beneath us comes into play, your proximity to the ocean, which is a good conductor of the current. Now, all these things come into play. So every different company have different procedures, quite significantly different from one company to the next. And they can be right next to each other even sometimes because of these different factors.
Yes, definitely. Thank you. Next question, Sue, possibly for you if you want this one. It's about geomagnetic storms and thermospheric neutral density and its effect on drag. And so the question is a little technical, but whether it matters more the energy of the particles coming in for a storm or the density of those particles.
I would just say the physics itself is complicated. When I talk about high energetic particle, we're talking about charged particles, right? We're not talking about some of this. But I think no matter what particle comes in, there's important things, the electric field in the background of the atmosphere that impose the whole energy called Joule heating into the thermosphere. So it really depends on how much the Joule heating, which combine the particle and the electric field, that goes to the system. So, just one of them might not play a big role, but depends on how they combine together. So it's complicated, but there is no which way goes to what, but it does need to consider all the physics behind it.
Okay. Any other additions or thoughts on that one? I was thinking it also has to do with, the size of the storm and satellites orbiting to lower latitudes as well. Bigger storms affecting more different regions, but that's a fun question maybe for afterwards too. Okay, great. How do you measure the speed of a CME?
Well, in the forecast office, we look for these through the coronagraph imagery. We measure them with a tool we have in there. It's an analytical tool, and that gives us an idea of the speed. And then that's interpolated into the model, and then we're looking and we would expect to see a similar arrival. So even though a CME may leave the sun at, say, 2,000 something kilometers per second, it may not arrive at that speed. It's going to slow down as it transits through space. It's only when it arrives at the satellite 1 million miles from Earth, that's measuring the solar wind, that we know what the speed is. That's going to be the same by the time it reaches Earth. And that's also we can identify how strong the magnetic field is within that CME and what we can expect here at Earth based off that. So that's one of the interesting, difficult things is we never know for sure how fast it's going to be because there's too many imperfections with the system that we have with limited data and resources until it actually gets to that warning level, that satellite 1 million miles away. So we can put out a G3 watch. It's really our best scientific guess. It may never reach G3 even though it arrives at Earth because it wasn't connecting, but we don't know that either until it's 1 million miles away.
Let me just add, because I did have that piece of this presentation on future things going forward. I just selected certain things. I couldn't select everything. One of the things I could mention now is this is a global threat. It requires a coordinated global response. So we're working closely with our partners around the world, and the European Space Agency are flying a mission that's planned for launch in 2031 called the Vigil mission. And it's going to be a spacecraft sitting off the sun Earth line at the Lagrange point 5. Now, it should be a great help in us better understanding the speed of the CMEs and when they're going to impact Earth. So we have high hopes for that mission, and it seems to be on track. And we'll be working with those folks, in fact, next month when we go to the UK to make sure that mission stays on track for the 2031 launch.
Yes, thank you. And that also dovetails into some questions in the chat about how different countries are coordinating their efforts. I don't know if there's anything more you wanted to say to that.
Yeah, I'll say that there's a lot of things. Like I said, okay, space weather is a global impact. Just a couple of months ago, we spent time in Australia and Adelaide working with the Australian government, who hosted a continent-wide exercise on a major space weather event. So those folks are taking it very serious, and they wanted us down there to get a sense for what's happened in the US from a policy perspective, so that maybe they could learn some of the best practices from us. And so that was a great engagement. And next month we'll be in the UK in Exeter at the UK Met Office. They are celebrating their 10th anniversary of the Space Weather Operations Center in the Met Office. And those folks are doing some great work as well. And we're all partnering together to learn from each other and to share the observations from one another in an effort as a global effort to address a global threat.
And we do that with forecasts as well. We're collaborating with these partners, Australia and the UK Met Office, for forecasts as well, so that we're all on the same page and we're all contributing to each other's forecasts.
Yeah, just add a little thing. We do need everybody's help to track satellites, right? We can't just have one country, because sometimes we rotate back to the other side of the Earth. So we do have the network working with different countries to track our satellites and spacecraft. We also utilize their ground-based data to give us real-time conditions. So it's really a global effort for some of these activities.
Yes, thank you. That seems like a great place to perhaps end this today, though there are many more great questions in the chat, and I don't know if there are any time to get some more quick answers in there from any of you on our panel. But Gideon, should I turn it back over to you? I could keep going, but
if you don't tell anybody, we can keep going a little bit.
Time.
Yeah, if everybody else is okay with that.
Yes. I wanted to ask if there are any questions that our panelists are burning to answer that they've seen, perhaps if you've had a chance to read any of them.
Seen the questions? No, I haven't actually seen.
Okay, then I'm doing a good job. There's some interesting questions about why SWPC uses KP in connection with the geomagnetic storm scales instead of DST. And there's also a question similarly, not similarly, but what would you say to shifting to a 22-year solar cycle instead of 11? So in this behind the scenes tour, I'm wondering if any of you might want to comment on those excellent questions.
I'll just make a comment about the K scale. The K scale has been around for many, many decades now. And as Sean said, it's the K5 is the G1, K9 is the G5. That has caused some confusion. So I had mentioned that the revision of the scales that's underway right now, we've identified. I highlighted just a couple of things related to the May event, but there's been many, many other issues with these scales, and that's one of them. The people are asking that question, Liz. They're saying, wait, now I'm seeing some products that say K scale. Our colleagues up north in Canada never adopted the US scale, so they make reference to a K8 storm. We're talking about a G4 storm. So we have introduced some confusion here. So that has been recognized, identified in this whole process of the revision of the scales. And needless to say, when our contractor that we're working with comes out with this summary of options and issues going forward, it's going to address that, Liz, and we'll see what we need to do to avoid that confusion that we're creating.
Yeah. And the DST is not something that we're using in the forecast office yet. I mean, these are things that are being looked at to improve the things Bill's talking about. But it does most certainly, that disturbance storm index, give us an indication of just how intense that was. Bill had it on his slide that give you an idea that Carrington event was at least 3 times stronger than what we experienced in May.
Yes, that's a really good point. Let's see. There's a question about whether artificial intelligence has been explored to help forecasting efforts.
Can take on that one, I think. I think Subsea does spend time looking into the options for that. I think one of the AI capability might be identifying certain features, and we already applied that in our website. We actually have a website that automatically identify different features on the sun. However, we do not have as much data as weather system. I mean, I know there are a lot of success in weather system. They're doing forecasting. We have relatively small amount of data. So using that data to predict things into the future is still very limited. So I will say, yeah, maybe in the future, but we currently have not seen much success in that. A lot of people predict things. They're like, okay, today is no storm, tomorrow is no storm. Well, 90% there's no storm, right? So is that a success, right? So I think to actually produce a storm and understand the physics behind it, we're still very limited using AI ML, but we are looking into it.
Yes, definitely. We want to use all the technologies we can and appreciate when they're appropriate. Let's see. There's a question after my own heart here. When NOAA, et cetera, are preparing post reports of geomagnetic storm impacts, are citizen scientists and the general public surveyed? Many farmers in Canada experienced issues with precision GPS during the May events. Maybe these anecdotal data may be valuable. The public may live in areas without reliable GNSS measurements and fill in gaps or provide ground truth to the science grade measurements.
You take it.
That was a long question. So, sum it up for me. Again, I'll give it a hack.
Are the general public surveyed in post reports? That was the question part. Yeah.
Yeah, maybe Bill can answer that part, especially from the 2003 storm. There was a service assessment that went out for that. So maybe Bill can talk about that in a second. But meanwhile, yeah, we are always trying to strive and reach out to not only our partners, but to the general public how we can, if they're able to provide any information through our social media platforms or through our customer support emails, to get and collect and understand what the impacts are. We heard a lot about these GPS use. I heard it firsthand from my farmer family in North Dakota that they were unable to operate their equipment during that storm. I mean, it happened. So we're always happy to get that input. We don't have a formal way of doing that to the general public at this time, but that is things that we're discussing. Bill, did you want to talk about service assessment?
Yeah, well, so I mean, the last thing you said is right. We just don't have a real any kind of a formal process. We certainly always embrace hearing about impacts, any kind of effects at all. It helps us. It helps justify our existence as to begin with, right? To recognize that space weather is having these different effects, but obviously we can look at our models too and see it helps to validate our models. We've got, for example, during the May event we heard a lot of reports from the airlines about losing HF communications, and they were telling us specifically the latitude of the impact, and we were seeing it a lot at 70 degrees north, but not so much at 60. And we're trying to capture that aurora oval on our products to show where the auroral absorption may be occurring. So having this kind of information, looking back at the model run for that given time when the degradation of the HF was occurring is great, right? We can do that validation. So that's very useful. What Sean mentioned was the service assessment. It's a National Weather Service process that we really, I think the 2003 was the only one we really did. It's because it's a big resource intensive effort to capture what happened, all the media engagement, all the impacts, the services, and assess how we did. We had talked during this, Sean was talking about it, he said, we didn't have a huge radiation storm. This was a big geomagnetic storm, the biggest since 2003. But the energetic particles, the S scale wasn't that big, and even the R scale, the solar flares, were nothing like the 2003 storms. So we just we determined we would not do a service assessment with the May event. But if it was much bigger, we would do something like that, engage more formally with people around the country and indeed around the world.
Let me add a few things. I mean, even though we didn't do the public survey, we do reach out to all the major GNSS receivers, manufacturers, right? So we got to realize that every GPS receiver come with different algorithms. So if you say this one is not working, the one next to you might be working. So I think there are a lot of different technique behind. Through public survey, sometimes we can come up with the solution, right? So we work closely with the manufacturers to understand what technique are being utilized so that scientists can build tools and models to mitigate those issues in the future. So sometimes it's great to have public survey, but sometimes it's good to go into deep dive into technology itself.
Yeah, that's a great point. And there might be a role for citizen science in that as well, with the different types of GNSS receivers too. So more fruitful discussions there, and collaborations with enthusiasts and the general public. Let's see. I had one more, perhaps one or two more here. How long can CME impacts affect the ionosphere? In other words, how long can those ions affected by CMEs last? I have heard that they can live up there without collisions or sinking for 1 to 10 years. Is that reasonable to you?
I will say maybe things are messed up, right? So ionosphere impact from the CME is actually short-lived. I mean, it's probably a couple of days, and we're not seeing things go beyond a few days. Things all calm down. But some of this particle from the coronal mass ejections goes into the radiation belt, and they stay long in radiation belt. And those are not ionosphere. Those are really go beyond plasmasphere and several Earth radius distance. So maybe those are different phenomena that it's being referred.
We don't have a tracker on those particles. We don't know exactly which ones make which collisions. It'd be pretty cool if we could track them.
I'll just add one thing to that. I mentioned that my brother-in-law was talking to me the day of the geomagnetic storming at those severe and extreme levels where he had to shut down his precision GPS operations. Well, then he called me, I think, I can't remember if it was the next night or 2 nights later, and said, when is this going to stop? And I was kind of mystified because the geomagnetic storms at those levels were done. But, quickly realizing after my surprise from this call was that, well, the ionosphere still has a lot to settle down. Perhaps that's still causing scintillation issues and stuff that could affect his GPS system. And in fact, for him, it did at a particular time of the day.
Mm-hmm. All right. I think there's a few more, but we probably should wrap up here. Let's see. Any more burning questions from anyone, any of our panelists? Final thoughts? Really appreciate all of these questions, and I'm sorry if we didn't get to some of them.
I will say, given this is an AMS, this talk here, that Sean has been doing some great work with the AMS and the broadcast meteorologist, communicating about this is not something that people understand easy, like hurricanes and earthquakes. So it is critical that we work with our colleagues, especially in the broadcast meteorology community, and the WFOs, the National Weather Service's 120 weather forecast offices around the country, and they are the central point for sharing information about weather, and we hope some of them are already doing it on space weather as well. So the local communities in the various states have that contact right at their doorstep, essentially, to get the information they need. So we very much appreciate the AMS and what the AMS is doing to help distribute accurate information during these big space weather events.
Yes, definitely. And this is a really cool community as well with the enthusiasts that they've started up here in the weather band. So happy to turn it back to you, Gideon.